start recording this, which I missed the first slide because we talked about Norman Borlaug, who won the prize for green revolution. Now, moving on to chemistry, I think chemistry is, I think only the biochemists would love this. So, because I had to really find the one that would be of general interest, because this is like the processes, even trying to read the details, I just got over it. Now, it's always good to start with fun, type of thing. So, and I'm sure all of us, at least, people who grew up here would be familiar with him, Tom Lehrer.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Okay, so that is the great Tom Lehrer, and I'm sure people remember him from the 70s. The same thing was done by Daniel Radcliffe, the Harry Potter kid, but his voice is not that good, so I'll just skip that, So he's on one of the, Graham Norton show in Britain, which is the popular show there, but he did, to his credit, he did memorize it and recited it, so you have to give him credit for that. Okay. And,
give a big shout if you.
Okay, now this is all of us remember this one. Okay, now this was before plastics. There was something else that was that was equally useful. Does anybody remember what that was? Bakelite. Okay, so and this was it's amazing fun researching some of this stuff. There's actually a big thing from coal and product and coal tar and other stuff that he synthesized the chemical, which was didn't catch fire and was, and that was the next was history. And believe it or not, in 1950, New York Times put this as an article, a chemical formula. Okay, this is C7H30O43, and this is the actual elements, how the carbon and hydrogen they swing are arranged in the bakelite. Okay, and so that is this. If the mathematicians would know that this is the sideway U it's like a set theory thing and equal to. So this was the formula that that he had, and all the symbols were created by Bertrand Russell and Whitehead in mathematics. So that's just we're digressing, and this is what was created. He was a Belgian chemist par excellence. He was already fairly wealthy because he had sold the photosynthetic paper to Eastman Kodak Company. Later on, they made celluloid, but that caught fire very quickly. So he kept working on finding the chemical, and there was a residue that was left after coal tar when he baked all the chemicals from coal tar, and the next was history. So, and bakelite became the workhorse of everything that was there, and before plastics took over. So before graduate, there was bakelite. So, and that's one of those inventions which was widespread but was never recognized as a groundbreaking event, by Nobel committee. So I thought, now obviously, there is enough things about Curie's that we have talked about. Now, whether she forms in physics or chemistry, take your guess. But that was the thing, that there was a really dangerous work that she did, and just isolated few grams of radium, and then the radium craze started, and it was so expensive that to generate things, she had to come to United States. So people raised funds so she could buy more radium. Okay. I mean, this was, so it was like a ground, people crowdfunding effort that was carried out so she could continue with the research. And her books are still radioactive after almost 100 years. So they have to handle with lead. And obviously she died of poisoning type thing. So there were the two elements that they discovered, and that was the start of atomic science as we know it. And then we talked about it in the discovery of neutrons, where her daughter and her husband, were also worked with radioactivity and were, reputable researchers, and they almost worked on chain reaction, but didn't quite spot it. They even missed the discovery of neutrons, but creating artificial radioactivity, they got the Nobel Prize. And now this was considered a very, groundbreaking discovery that everybody had pleaded, said this is, this can be, don't let this go in the hand of Germans, but they published the articles anyway. But already the Germans already were ahead of it, and that was the history of the atomic project that we talked about, And so this was. Now, Marie Curie, on a personal note, she had an affair after she got divorced, after her husband had died, and that was, backfired on her, for the era of the time, so to speak. So she had, as being a woman, her personal life was held against her type of thing. So, and so this was, and finally, this idea was sent to a eccentric Hungarian who was kind of all over the place, starting from Hungary to Germany to London. And he was the one who was actually the kind of came up with the idea of that nuclear fission can be used to make an atomic bomb. And he went to the British government and said, well, you have to classify these documents before the Nazis get it. And the Brits did, I think, classify their documents. But by that time, everybody knew about it from the article. So the knowledge was very, very widely shared. And the rest is history for the project. Now, the good and bad goes evil, like, I don't know how many of you have heard of him, but Haber-Bosch process. Again, along with Borland, this is another process that changed the history of starvation and food production all over the world. Okay, Fritz Haber was a Jewish chemist, and at that time, for fertilizer, guano was imported from South America, and to increase grain production, and there was a natural fertilizer type of thing. So there was always this dream of fixing nitrogen from the air, but nitrogen is kind of an inert element. It was, hard to doesn't react that easily. So Fritz Haber's discovery was with high pressure and with catalyst, he was able to react nitrogen gas and hydrogen to create ammonia. And that was a groundbreaking discovery. He was a chemist, so his work was on a smaller scale. This was further expanded by a chemical engineer named Bosch. Okay, and that's the foundation of the Haber-Bosch process, and that was adopted all over the world. And by that time, the guano thing was import was dwindling down, and that changed the fertilizer industry and dramatically. And then again, and that and the nitrate production and other things. So and that had a lot to do with the fructose also, because during the wartime, nitrates were necessary for gunpowder and other things. And after the Second World War, that was all changed to producing fructose, and that just created the obesity epidemic. So I'm digressing, but so that's how one type of chemical production can backfire. So now, interestingly, Haber-Bosch was, even though he was Jewish ancestry, this was his statement, the father of the chemical warfare, that during the war, science belongs to the whole world. But during war, the nation state comes. So he was a German patriarch, type thing. So he was the founder of chemical warfare. Okay, so he discovered all the mustard gas and chlorine gas, and was sent to the front to see how how this would react. And the first time during the First World War. So on one hand, he saved hunger in the entire world. On the other hand, they were like, this was a totally new warfare. And the earlier agreements that were done in 1899 were totally brushed aside. And the chemical warfare was the biggest, was the horrible way of people to die, during the First World War in the trenches. Okay, and again, that's an interesting history that, that the masks were provided for some soldiers, but not for the others, Okay, and there's some interesting history as how the Indians who were working for the British government, so they were not given the proper mask, and they were just totally exposed and just died as cannon fodder. A lot of them, in the trenches. Okay, and so this is the chemical warfare, so this was the statement, and here he is, on looks like the evil in persona, so to speak. So, and unfortunately, even though he had done so much for Germany, during First World War, when it came to 1933, he became a persona non grata, and fortunately, he died, in 1930. So he didn't end up in the camp, and he was trying to run away from the Nazi Germany, and it just, it was a tragic end. Okay, and even his wife actually divorced him because she did not want anything to do with all this killing products that he was devising, chemicals that he was devising. So it's another story that, and I'm sure, you recognize Ethel, so this was the one person who did more to harm the environment, was a chemist par excellence named Thomas Midgley. He doesn't figure much in, obviously didn't get the Nobel Prize, but, with the rise of automobile industry, the knocking was a big problem. So, he was working on to see how to prevent this and prevent engine damage. And he had worked on various other chemicals, but some of the elements were quite expensive. So finally, he stumbled upon, I'm trying to think which one he had used for it. I'm sorry, I've now lost it. Selenium. He had tried using selenium with benzene ratio to prevent knocking, but selenium was rare and expensive. So then he later on settled on the cheap element lead, and that was the rise of the ethyl corporation. And now at the same time, a woman physician who is kind of the giant of occupational medicine named Alice Hamilton had already pointed out that, using lead is dangerous, and even working with lead, it's a serious health risk. But the ethyl corporation had deep pockets, and the use of lead continued for almost 40 years. And they kept lowering the standards, but finally it took a long time for it to be eliminated. Okay, so lead, and to prove that he was in the pay of the company, so he even actually drank the lead contaminated water, and eventually he died of lead poisoning himself. But he kept all his life, he maintained that lead is not dangerous. Not to be outdone, he had also discovered carbon fluorocarbons for refrigeration. So that had, now at that time too, we have to say that they were unaware that had a damaging effect on the ozone. And it took until 1980s for a guy named Crutzen to say that yes, the carbon fluorocarbons, can combine with oxygen and make a hole in the ozone. So the chemical reaction that takes place, the carbon, the ozone layers can be created, in type of thing. So it took and you can see for the carbon fluorocarbons formula. So this was the Ethyl Corporation and Thomas Midgley. Okay, and I think those of you who read Bill Bryson's book, there's a nice chapter about his discovery. So I just thought that, and so this was, so later on, finally, Paul Cruzen and other colleagues recognized, and it took 1995 to say that, that the ozone chemistry, atmospheric chemistry, the science, it took almost, a whole generation to get worked out. So that was an interesting tie-in to Nobel Prizes, Okay, now this is, and now we talked about Niels Bohr as the founder of quantum physics. Okay, now obviously he had the formula of electron shells, And based on the genius of Mendeleev was that based on the gaps in the atomic number table, he had predicted that there should be an element. Okay. And this was predicted that there was a gap at atomic number 72. Okay. And simultaneously, Niels Bohr, by this time, he was the big giant in physical chemistry. So he had associates named, Koster and von Hevesy, okay, and they were working in his lab, and they were able to discover the new element, okay. Simultaneously, some other French people, chemists were working on it, and just you couldn't plan it better. When Bohr was receiving Nobel Prize, he got the telegram that they had isolated this element. So he was able to state that the idea that was proposed based on theoretical basis was actually shown. And so and his honor, it was named hafnium. Okay, hafnium is the Latin term for Copenhagen, where the Bohr's Institute was. So it's a remarkable story. You couldn't, I mean, Hollywood couldn't plan it better. And I just thought, out of interest, I'll throw in this slide, that this is the metals inside your smartphone. And this was, phenomenal as to how many, and I think you can just zoom on it, at your convenience, as to how many small, the rare earth atoms are inside your small cell phones. Okay, I'm trying to see if I can zoom in on it type thing. So, okay, see, and prosodium, you can just, you can read it, type of thing. So, and these are all gadolinium, terbium, these are lithium, cobalt, nickel, okay, lanthanum, these are extremely rare elements. So, so no surprise that the Chinese have the monopoly on it, okay. And so this was an interesting thing as to how chemistry is all around us, I think so. Okay, and now this is, like in physics we have Albert Einstein, in molecular biology we have Crick and Watson. In chemistry, in 20th century chemistry, if you had to put one person, this has to be the man, Linus Pauling, okay? And he came in from a modest background, but was absolutely genius. He grew up in Oregon, okay? And John's gone to, I think, University of Oregon, and they have a big Linus Pauling lectures. And by age 18, he was already, a teacher and got a very early PhD and had later on moved to Caltech, and earlier from experimental chemistry, he had traveled to Europe and absorbed quantum physics, met all the people who are doing pioneering work on quantum science, and came back to Caltech and never moved away from Caltech. He never got into this theory about the classical physics and quantum physics, but he just worked on the quantum idea of uniting chemistry and physics. So the two disciplines were united. Okay, and this has, and these are the chemistry that worked out, type of thing, the 4-carbon methane, and theoretically he had predicted xenon, which is inert gas, can be combined with hexafluoride. You can see how, and so he had predicted that. Now this did not go well with the founders of crystallography, Sir Thomas Bragg. Okay, they just initially suspected that Linus Pauling had stolen his ideas and was taking credit for it. But obviously they were wrong. Linus Pauling was way ahead of everybody, and he was prolific in terms of lab work, and people were not even able to interpret his papers. He was so productive, and eventually had produced the classic tome of The Nature of Chemical Bond. And the book is, was published in 13 languages, and like the Bible of physics. I'm sorry, go ahead, please. You're muted, sir.
Yep, okay. I've got a quick little story, if you could indulge me. That
go ahead, please.
In 1977, when I was in graduate school for physics, and I was actually trying to specialize in biophysics at the time.
Oh.
And that was at University of South Florida. I had heard about the quantum physics and biology symposium that was held in Woods Hole, as well as I think it was either every other year, I forget the frequency, also at Sanibel Island in Florida. And I was solicited to be a part of the small group of graduate students to help organize and conduct the Sanibel Island Quantum Physics and Biology Symposium. We were staying, I can't remember the place, but it was a little like cottages, you know, beach cottages on the beach. And there was a small building that we had blackboards set up, and it maybe had room for about 50 people, something like that. I got to meet Linus Pauling there. I got to meet St. George there, the inventor of vitamin C.
Oh yeah, the Hungarian.
And everybody was so excited about the increased use of computers for being able to help do calculations and predictions to try and model various chemical compounds together and things like this. Well, I'll wrap this up with one quick little funny aside that I found.
Yeah, please go
I
ahead.
was during one of the breaks, I was sitting poolside, and next to me, I started chatting with one of the fellows there, and it turns out he was head of research for Eli Lilly. And I was so naive. I wanted to strike up a conversation. I said, well, how many good drugs do you guys come up with a year? and he laughed and he said, if we come up with a good drug every like 8 to 10 years, that's really good. And I was shocked, and I said, oh, well, how do you know when you have a good one? And this is the one I never forgot in my life. He said, if it's 10% better than a placebo, we knocked it out of the park. And I said, 10% better than a placebo? He said, hey, don't knock it. Placebos work 30% of the time.
Yeah, amen. Yeah, absolutely. You know, that's just like, as a physician, I can second that, no question. Yeah.
As long as you believe it, right? You got to believe it.
Right. I think, you know, it's like, and I think I have his name in the breakthrough prizes. You know, I think I think I know who you're talking about. He's a chemist who actually was the head of Lilly. And so he went to the industrial side. I think I can't take the name, but I mean, I have tons of slides. I looked through the new thing called the breakthrough prize that you may not, I presume not all of you know about it. Breakthrough prize is the new thing that inspired me to do this, because they're trying to correct all the deficits of Nobel Prize. They're not limited to 3 people. They're going for people who don't have to wait for 50 years. You know, for example, the CRISPR ladies got the breakthrough prize in 2015. The Nobel was in 2020, and their paper was published in 2012. So within 3 years, they were recognized, and that prize is a lot more valuable, $3 million. And that is not, and this is like the Silicon Valley people, they have, you know, more money than God, so to speak. So that is like, you know, and include mathematics also, life science. So it's a new thing, it's a 21st century Nobel. And so I have a tons of slides. In fact, I put in a whole PowerPoint for that, you know, which I will share with you, all of you, type of thing, just, you know, including, because some people just never get the nod. For example, Salk and Sabin, they are saved so many billions of lives with polio vaccine. They were never recognized. Okay, Thomas Edison never recognized. No. So so this is Linus Pauling. His book is, I mean, Peter may have read the book Nature of Chemical Bond, but I mean, I'm just vaguely aware of it, you know. So, and not to be outdone, after physical chemistry, he had written more than 1,000 articles, and, you know, divided the valence bond theory and a concept of electronegativity or orbit resonance of the chemical elements. These are all the concepts that are the bread and butter of inorganic chemistry. Not to be outdone, you know, that he continued working on molecular biology. It described, what is known as the alpha helix protein. Okay, so then he branched on into molecular biology, and he was the first one to determine the protein, work on the early hemoglobin, and discovered the deformity in sickle cell. So branched out into medicine. So you can just see his impact was then worked into metallurgy, mineralogy, it's inorganic, organic, so he worked on, inorganic substances like topaz, mica, and immunology and neuroscience. So there's not a single branch that he did not have impact on. But I know, but like it happens quite often, or for whatever reasons, he was a big believer in vitamin C for things, and became, and those results that he thought he had succeeded were never duplicated. Mayo Clinic did a study with his protocol and never panned out. So again, and even in the early 50s, he was, out protesting against the atomic weapons, and he was invited to work on the Manhattan Project, but he said, nope, I don't want to get out of Caltech. So he didn't want to live in Los Alamos, but he did work on the war projects, so he is, really a man for a giant in the field. So enough eulogy from, and then this is a note that you may not know that, but they were working on the structure of a DNA molecule, and he had hurried and published the, like a like a three elements winding together, that thing. And he had made a basic mistake in physical chemistry. He had put the A, C, G, and T on the outside, which had a negative charge and repelled. And obviously, in those days, there was not that much peer review, or nobody was able to interpret. So Nature magazine published his article. Okay. And when Watson and Crick read this, said, this is an elementary physical chemistry mistake that the giant in the field made it, And so, and they started working. So, okay, we should put this ACGNT on the inside and the sugar phosphate bond on the outside. And obviously that worked. Okay, so even the greatest physical chemist can make a basic error. And the article got published. That is the irony of it, I mean, nowadays it were not even past the first editorial review, So it was just interesting how in the 1950s, how the process was, things. And even now, I think, whose name is on the article, his acceptance would happen. I mean, if you send an article from USF, your chance of getting accepted are pretty slim, as opposed to coming from Stanford or other things. So, okay, and now I think I summarized the article here as to Nobels through the years. Hormones are extremely popular, and it just goes from bottom onwards. I think from the various hormones, adrenocortical hormones, which are the cortisone, which is the disease that Kennedy had, insulin, okay, and prostatic hormones, radioimmunoassays, so prostaglandins, cholesterol, all of these. I have individual slides when I did the class on medical Nobel Prizes, so I have a lot more details on this, but this just summarizes that hormones and body chemistry is extremely. Now, whether this falls into medicine or chemistry, it's a guess as to how that falls apart, So some people got the Nobel Prize for chemistry, but some got for medicine. For example, Goldstein and Brown, who did the work on cholesterol LDL receptors, they got the Nobel Prize in medicine, Okay, but it all just, basically it's chemistry and physiology. Okay, all right. So now, we talked about, the transistor, Nobel Prize, which was given for that. Okay, John Bardeen got the double Nobel Prize in chemistry, along with Marie Curie. Frederick Singer got the Nobel Prize twice. One of the unique persons, was a very unassuming Englishman chemist. Okay, and a crystallographer to start with, and worked on the chemical structures of insulin in the beginning, and crystallography. So that was his first Nobel Prize for, crystallography has been the forays of English chemistry, starting from Bragg, father and son group that we talked about. And there are various other crystallographers were, giants in their field. And Frederick Sanger worked on it, because insulin is a huge molecule, with very complex structure. And it took some, really remarkable piece of patience to determine this structure. So Frederick Sanger was, and then later on, he moved on to, the molecular biology, worked on RNA molecule, which is a smaller and easier molecule to determine. And later on, discovered by putting radio tag A, C, and G and T. Okay. These are called, adding the agents A, C, G, and T. See the radioactive color tag thing, and as to how they migrate on X-ray plates. And creating chromatograph, laser detection. So this is, like depending upon the weight of these nucleosides, how they would migrate, on electrophoresis, and they're detected. And so this was the early method of determining, the RNA and DNA structure. So initially they worked on RNA molecules, and they worked on, something called mitochondrial DNA, which is relatively small and was easier to determine. So, and along with another American molecular biologist named Paul Berg, this was the accepted method, and this was the method that was used for the Human Genome Project, which was, took, $3 billion and almost 8 to 13 years. So that was Frederick Sanger's, and his mentors, again, were the giants of crystallography. The Nobel Prize 1960. Now, a chemist named Walter Libby, who came from an humble background, growing up in small town, and after his PhD, he worked with, with the atomic project as a chemist, and worked with, Harold Urey, and then after the end of the Manhattan Project, moved to University of Chicago. And he was given a project now by this time, after the Manhattan Project, isotopes were, the different isotope structures were recognized, and based on the carbon-14 isotope, he worked on the method as to how it decays in natural elements, such as, archaeology, trees, plants. And so that was the way to, for example, how the sample is prepared and chemically dissolved in benzene, and depending upon the half-life, as the carbon-14 half-life is known. So based on the amount of, after the animal dies, the metabolism stops. So that's how they're able to date, the age of the rock and the half-life of decay that was known from the accelerators and Lawrence Livermore Laboratories work. So this was the groundbreaking method that was, let's see if I can play the video with this.
It is until a singular discovery in chemistry changed the course of history. Welcome to The Day Tomorrow Began, the genesis of world-changing ideas from the University of Chicago. In the 1940s, the discovery of a new isotope, carbon-14, was of particular interest to University of Chicago chemist Willard Libby. Libby was the first to suspect that all living organisms would absorb carbon-14 from the atmosphere. After the organism dies, the carbon-14 slowly starts to disappear, like a countdown clock. Libby theorized that by measuring the carbon-14 left over, he could determine the approximate time of death. To test this, Libby measured samples of known antiquity: an Egyptian funeral ship, a Dead Sea Scroll, and a charred piece of bread from the ashes of Pompeii. It worked. The radiocarbon revolution had begun. Carbon-14 dating transformed fields from archaeology to oceanography. It proved civilization originated simultaneously around the world and determined when the ice ages began and ended. Today, carbon-14 dating is being used at the University of Chicago and around the world to power new.
Okay, so that was the big start, and the ideas were known from cosmic rays, which generates neutron, and the reaction that takes place between nitrogen and C14. So the half-life was known as almost like a 6,000 years, and but there is a limitation that for the older elements it's. But now the technology has been incorporated to different elements which have a lot longer half-life. So this is the start of actual dating all the fossils that can be
Scientific.
okay. And now again, the another important discovery, which is the staple of forensic medicine, was discovered by a somewhat outside the norm a guy named Ray Cary Mullis, who worked for Cetus Chemical Corporation, and based on DNA, like just simple heating and cooling, came up with a method of PCR, or which is called polymerase chain reaction. So what he did was, just like when the DNA molecule is heated, the two strands separate, and then and afterwards, it's cooled off to 55 degrees centigrade, and by this time the DNA primers, which the AC and GAT segments were introduced. So it starts multiplying in the test tube, okay, and it becomes exponentially if the same process is repeated, broken down, multiplied. So you go from 2 to 4 to 8 to 16 to 64. So after running about 10 or 15 cycles, you have tons of fragments that are available. So the smallest amount of sample can be later on identified, with technology. So this was the PCR, method, and that's just absolutely revolutionized crime detection and chemistry per se. And then afterwards, and the story is that he was high on LSD or type of thing and was driving on California highway. That's when he got the idea and just wrote it down quickly. And then he was employed by the Cetus Corporation. So in terms of who gets the award and reward for it, as to the patent rights, so there was a lot of controversy. And later on, and after he won the Nobel Prize, he kind of went off the tangents and became a believer in astrology and climate denier and all sorts of crazy things. So somewhere along the line, the LSD caught up with him. Okay, so that's an interesting human interest story. Another crystallographer par excellence, it was one of the first women to get a Nobel Prize in chemistry, and crystallography, was Dorothy Hodgkin. And she also was one of the first ones to get the, Copley medal that we talked about earlier. And she was mentored by, other, well-known crystallographers in Cavendish lab. A guy named J.D. Bernal discovered the, and it required again the patience of a saint for determining crystallography by X-ray technology, determined penicillin, vitamin B12, and even more refined structure of insulin. So she worked on all of these, and obviously was rightly recognized. Now she was married to her husband, who was a the Communist Party member. So for visiting United States, she became again undesirable person back in the 50s. Okay, and she was one of her a student was a woman named Maggie Roberts, later on to be the Prime Minister Maggie Thatcher. Okay, so the Brits would get a kick out of it. Okay, and now this is almost a head-spinning quiz. I'm not even going to try to explain this. I think maybe Peter can be brave enough to try to explain this. This is the something called the chemiosmotic theory. This was proposed and proven experimentally by a guy named Peter Mitchell, who was independently wealthy and worked outside the universities, not at Cambridge or Oxford, but he has his own self-funded lab, I think somewhere near Manchester. And he had an able assistant who was a woman who was a better experimenter than he is. But his ideology was to prove the chemical structure of the metabolism of photosynthesis, okay, and mitochondria, as to how, the oxygen and metabolism takes place. Something called the proton gradient across the semi-permeable membrane that takes place, as to how, and these are the various complexes that form from, and this is how the oxygen and the photosynthesis metabolism that takes place in plant. Okay, and initially this was a total paradigm shift, or has to do with something called the electrochemical gradient, and it has to do also with the formation of ATP, the basic workhorse of biology and energy, and this is called proton transfer. And there has been some question with the classical electrochemical reaction, and a quantum phenomenon may have something to do with it, as we were talking about earlier about how quantum is incorporated into biology. I forgot to give the examples of this last time, that some of you may know about this, how the birds navigate from the Arctic Circle all the way to the tropics. They end up without any GPS, they have cells, in their brain and in their eye. They respond to the Earth's magnetic field, and that mechanism may have to do with quantum phenomenon. And that has been well known, that it has been experimentally proven. Okay, people created artificial magnetic fields, had they rotated it, and how the birds, flight moment change. So this has been done by some. So this is not just somebody's concept. So, okay, the second idea where quantum may be related has to do with our sense of smell. Okay, and the example that is given is that cyanide and almonds. Okay, and they are different chemical formula in terms of their chemical structure, but they're both give similar smell. So that may be a quantum phenomenon in your nose, because smell goes directly from your nose to your smell receptors in your brain. It's a direct way from your nose. So that may be an example of quantum phenomenon. Okay, and then again, the metamorphosis of a tadpole that take place, that may be an example of a quantum phenomenon. So biophysics, may have a lot role, and a guy named McFadden and Jim Al-Khalali, back about 8 years ago, had written a whole book on quantum biology, and this phenomena of mitochondrial cellular respiration, that may have a lot to do with, and I think there's an English, physical chemist guy named Nick Lane, that who has done a lot of the work, and he is still a very active lab at University College of London on determining the origin of life. So how the mitochondria, the energy is a big factor. So that may be tied in. So what Rex was talking about earlier. So that is, the research is progressing a lot more than what was there back in the early days of 70s. Okay, so and one interesting research for chemistry is something called the buckyballs. A lot of you grew up in the 60s know about the Buckminster Fuller, who was an inventor par excellence, and had, his finger in each about odd field. And during the World Fair, the Buckminster Fuller structure was created. And this idea of the ball structure of 60 elements of carbon, C60, was proposed back in the 70s. But finally, this was proven with more scientific basis, back in the 80s by guys named Harold Kroto, who was Japanese, and a couple of the other guys. And this was not just a chemical curiosity, but has a big relation with what is known as the nanotubes, which are useful for electrical conductivity and chemical and photovoltaic cells and various pharmaceuticals, soaking up free radicals, which can be harmful to the human body, and useful for MRI. So this polymer C60 structures, so those are the ones that were recognized, as, and the name that is given in the honor of Buckminster Fuller is called fullerenes, the round molecule of 60 balls that he's holding you can see on the side. And so there are the 60 molecules, that's the carbon strength, that is, so that I just thought of was really of interest. Another chemical discovery that may be worth noting is this one. Let's play this for a little bit.
Roger developed variants of GFP that were brighter and came in a variety of colors beyond green.
And we then had to come up.
I'm sorry, I didn't.
A protein in the jellyfish that glows bright green under a UV light. It came to be known as the green fluorescent protein, or GFP for short. Years later, a researcher named Martin Chalfie heard about the green fluorescent protein at a conference.
I got very excited and immediately ignored the rest of the seminar and just sat there fantasizing about what would happen if we could possibly take this protein and allow it to be made inside of our worms and look at how things were being made.
At the time, he was studying these small organisms called roundworms. There's all this activity going on inside of an organism that's completely invisible to researchers, even with a microscope. Martin realized that he could use GFP as a way to map the inner workings of a roundworm. This was a big deal. Like the invention of the microscope, the X-ray, or the MRI, green fluorescent protein opened up a new world for scientists. They could suddenly see what was happening inside of a cell that had been completely invisible before. But the green fluorescent protein wasn't perfect. It would lose its glow over time, and it wasn't the ideal color for all studies. Here's where UC San Diego researcher Roger Chen enters the story. Roger developed variants of GFP that were brighter and came in a variety of colors beyond green.
And we then had to come up with names for these, and upon examination of the Crayola website and other consultations, we realized that the simplest, instead of giving them numerical names, were names like monomeric banana, orange, tandem dimer tomato, tangerine, etc., all the way out to plum.
This beach scene in a petri dish was made using some of these colorful variants in Roger's lab at UC San Diego. But these glowing proteins aren't just pretty. They allow researchers to mark and observe more than one thing at a time. Researchers at Harvard University use them to color nerve cells in a mouse's brain to see how they form a network. The experiment was called the Brainbow. Today, scientists at some of the world's leading hospitals use green fluorescent proteins to study all sorts of diseases. UC Davis uses it for HIV research, while UC San Diego uses GFPs to track breast cancer tumors, and Mass General has used the technology to better understand Alzheimer's disease. When Osamu Shimomura began his research,
Okay, so this was, and we have seen the sections of brain, mouse brain. Each an individual cell is kind of tagged, it's like a color view of the entire brain of the so-called pyramidal cell and the glia cells and everything else. So it's just a phenomenal way to study the things. So this is like the workhorse of cellular biology.
he didn't
Okay, now this was, like the ribosome are, like the structures of the protein, which has to do with the transfer RNA, mRNA. That's how the genetic code from DNA to RNA to protein, it's like, because DNA just stays inside the nucleus. So the basic, things were. Now somebody had to work on the structures of ribosome, and there are different, the two types of cells, the prokaryocytes, which don't have nucleus, and eukaryocytes, which have the nucleus. They have different size, different types of ribosome proteins, okay? And there are different molecules, and these are measured in this. S means something called Swedberg, so that has to do with the atomic weight. And the race was on to determine the atomic structure, the structure of these units. And so people who worked on it, were Ada Yonath in Israel, and her colleagues, and Venki Ramakrishnan. And Venki Ramakrishnan, we mentioned him earlier during the Royal Society, that he started out with physics, didn't find a postdoc position, and after his PhD in physics, switched to biology and worked on, determining crystalline structure of ribosome at Cavendish Lab at Cambridge, and went on to win the Nobel Prize. And he's Asian Indian, and he went to the same university where I got my MBBS degree. Okay, and he was there just a couple of years ahead of him, and so this was, now adding up these different units of ribosome units. I'm always flummoxed as to they don't add up to be 80. So how'd they get the 80 number? That's beyond me. That's why I thought biologists don't do math. And if anybody can figure that out, let me know as to how they know. When you add up the number, they don't add up to be 80. So how did they come up with 80 Swedberg, which is just beyond me type of thing. So I'm still scratching my head as to how that comes about. Okay, now this is, I think that we're writing up with chemistry basically, and then we'll go into medicine. Batteries have been this thing, and this is, this is one of the oldest Nobel Prizes, John Goodenow. Okay, in 1980, he worked with lithium batteries with the cathode ray of cobalt, and that can house lithium ions, and the voltage, was better than the old nickel cadmium batteries and the lead acid batteries. He worked on it, back a long time ago, and finally received the Nobel Prize at age 97 in 2019. And he just died a couple of years later. So, okay, so this was the big discovery and it's changed the, fuel cell industry for the long time. So he was born in 1922 and died at the age of 101 in 2023. And this is the principle of the lithium ion, as to how zinc alkaline battery, the electrons are pulled one way or the other. The lithium cobalt oxide pulls the electron from the graphite solution along, and then from the bond, which is reversible type of thing with recharging. Okay, so this is the basic principle of it, and I think you can look it up in more details if you're curious. And that is the workhorse of everything that we use, and Sony Corporation flew with it and made it a lot more, and it still has the potential for recall sometimes due to fire hazard. Sometimes even some people's Tesla cars have caught on fire. So it's still, so the search is on for the cheaper source. And I just read a book called The Material World about the essential element that made the modern world, starting from cement to iron to everything else. At the last at copper, and the last chapter is on lithium. So the big race for finding lithium that has made Chile very rich, because that's where the biggest mines are, and of course in China. Okay, and the final big Nobel Prize, which I think I'll just see, and plus CRISPR has nothing to do with Kentucky Fried Chicken, by the way. Okay, it stands for an abbreviation: clustered regularly interspersed short palindromic repeats. That's what the whole mouthful stands for. And this little video just explains, and the idea was discovered back in bacterial cells. A virologist was working, and biochemist Jennifer Doudna, they met together at a conference in Puerto Rico, and they decided to collaborate. And the ideas were earlier worked out by a Spanish scientist who had actually done the work on CRISPR molecule while on vacation and then several people were involved, and David McConnell had written a biography of Jennifer Doudna, and in which he tells the story of as to how many people are involved. And there was a huge controversy that started about who should get the patent rights, because these two ladies had worked on prokaryocytes, because they were bacteriologists by training, and they didn't work in mammalian or in eukaryotes, the cells which are more difficult to work on. And so the big patent fight went on with MIT as to who would get the patent right, and the cases went to the court, and so that's it's a big story as to how the money was involved with these big universities on East and West Coast. Now let's just explain how the CRISPR works.
It's twisted into a double helix and held together by a simple pairing rule. A pairs with T and G pairs with C. Our genes shape who we are as individuals and as a species. Genes also have profound effects on health, and thanks to advances in DNA sequencing, researchers have identified thousands of genes that affect our risk of disease. To understand how genes work, researchers need ways to control them. Changing genes in living cells is not easy, but recently a new method has been developed that promises to dramatically improve our ability to edit the DNA of any species, including humans. The CRISPR method is based on a natural system used by bacteria to protect themselves from infection by viruses. When the bacterium detects the presence of virus DNA, it produces two types of short RNA, one of which contains a sequence that matches that of the invading virus. These two RNAs form a complex with a protein called Cas9. Cas9 is a nuclease, a type of enzyme that can cut DNA. When the matching sequence, known as a guide RNA, finds its target within the viral genome, the Cas9 cuts the target DNA, disabling the virus. Over the past few years, researchers studying this system realized that it could be engineered to cut not just viral DNA, but any DNA sequence at a precisely chosen location by changing the guide RNA to match the target. And this can be done not just in a test tube, but also within the nucleus of a living cell. Once inside the nucleus, the resulting complex will lock onto a short sequence known as the PAM. The Cas9 will unzip the DNA and match it to its target RNA. If the match is complete, the Cas9 will use 2 tiny molecular scissors to cut the DNA. When this happens, the cell tries to repair the cut. But the repair process is error-prone, leading to mutations that can disable the gene, allowing researchers to understand its function. These mutations are random, but sometimes researchers need to be more precise, for example, by replacing a mutant gene with a healthy copy. This can be done by adding another piece of DNA that carries the desired sequence. Once the CRISPR system has made a cut, this DNA template can pair up with the cut ends, recombining and replacing the original sequence with the new version. All this can be done in cultured cells, including stem cells that can give rise to many different cell types. It can also be done in a fertilized egg, allowing the creation of transgenic animals with targeted mutations. And unlike previous methods, CRISPR can be used to target many genes at once, a big advantage for studying complex human diseases that are caused not by a single mutation, but by many genes acting together. These methods.
Okay, so you get the idea type thing. And this was done by a scientist, in 2 newborns, okay, to remove the HIV gene that gives you protection, from HIV. So he did what was called as germline surgery, which is a big no-no. And he was, initially the Chinese government said, oh, wow, he's very unique and has done the work type thing. But then later on, all the genetic community was just horrified that this is altering the human germline so that could be transmitted. And he was, it was criticized for doing his work, and the Chinese government came down on him. And because so there is like a moratorium, and becomes a very ethical consideration as to whether human germline, which is if you do it inside the egg, then it can be transmitted further down the chain, and you could alter the human genome code for forever, so to speak. So that was a big, the big moratorium on it. And it may be, now it is permitted for some rare diseases, such as mitochondrial diseases, because mitochondrial DNA is very small. If there is abnormality, that can cause some horrific diseases. So UK has allowed, genetic editing for mitochondrial diseases. So it's a big cutting edge scientific field that we did in a class. Okay. Okay. And so these are the various elements that are named after various scientists: Niels Bohr, Curie, Einstein. Just for curiosity, I just threw that in. Okay. And Glenn Seaborg was one of the big giants of early chemistry, and he has discovered this many elements. So, all the rare elements, which are beyond the naturally occurring 93: americium, curium, berkelium, californium, einsteinium, fermium, mendelium, nobelium, seaborgium. So, and he was a giant in the field. He was the Atomic Energy Commission, and he actually had succeeded in converting bismuth to gold. Okay, so the real idea of so-called philosopher's stone, that people from the ancient times had the dream of converting, a rare common metal to gold, he actually succeeded, but it was outrageously expensive. So don't have any hopes of that. That's going to become you can buy cheap gold that way. Okay, so I think we're done with the chemistry type of thing, and this is another thing for the sake of time, I'm going to skip, called directed evolution, which is the more recent Nobel Prize, which is working on enzymes and to speed up the process and protein engineering. There was a scientist named Francis Arnold got this thing. So because evolution is a very slow process based on enzyme, so they worked on something called the directed evolution. So speeding up the process of natural evolution about 5,000 times. So that was one of the things.
Francis Arnold.
Okay, and the last most Nobel Prize is something called quantum dots. That is this year's Nobel Prize, which are nanotechnology and material science related, which are, so that was the most recent prize. But I think for sake of time, I think I'm going to skip over that and jump over to medicine. Okay, all right, and in the medicine, all the categories that have been recognized, are vaccines, vitamins, antibiotics, genes, genetics. So it goes through fashion various times, okay. And this was a commercial that during the Super Bowl, Pfizer did, type of thing about. And there was pretty. So this was a commercial during Super Bowl about Pfizer's promoting science, and they were promoting their, COVID vaccine. That was the big, their big home run. Okay. Okay. And now the early days of chemotherapy, because obviously syphilis was a pretty serious disease back in the early 20th century, and people were trying all sorts of things, and it was considered a newer disease. And when German chemistry dyes became popular, they were checking out various dyes. And an arsenic compound named salvarsan was discovered by Paul Ehrlich, who was an immunologist in the early days. And this was the dye that actually worked on syphilis and was so important because syphilis, for whatever reasons, was a very serious disease in the early 20th century. It caused insanity, called the general paralysis of the insane. People really went, like caused serious dementia. It also caused aneurysm inside the heart, and it may be coming back now, I think so, but at least syphilis finally the virulence decreased. So, but this was the big prize, was made into a movie by Hollywood back in the 30s, Paul Ehrlich. Okay, and immunology was coming into existence, so it has been recognized for a lot of Nobel Prizes. Paul Ehrlich worked on and along with the Russian scientist named Ilya Mechnikov. Okay, so this was. And then wars are great for research. So during war, people who were, had damage from shells and other stuff, their skin was sloughing off. So doing skin transplant was important. So Peter Medawar, who is the British immunologist, worked, so how the grafts are rejected. So that was the founding of the early days of immunology. Okay, moving on further down to medicine. Okay, and finally, this was the big problem for the, further immunology was then something called the monoclonal antibodies. And the research was done in Britain, okay? But somewhere along the line, with the laid back attitude, they published the articles in Nature and forgot to get the patent for it, okay? And the savvy US-based scientist named Wistar Institute in Philadelphia, they managed to get the patent a few years later, based on their shared technology. And needless to say, the British government was not very happy with not patenting it. So a guy named Milston and Kohler worked on something called the monoclonal antibodies, which has become the workstay of targeted chemotherapy now. So the technique was developed in UK by what they did was, by created an artificial tumors on animals called hybridoma. And based on that, they were able to, generate massive amount of antibody reaction. Okay, and so that was one of those big let down. Okay, now the most killing organism in human being is not a bacteria, not syphilis, not COVID by any means, not smallpox, but a tiny mosquito. Okay, and one of the earliest Nobel Prize was 1902. By a British physician scientist who was working in Calcutta, and had with microscopy had done dissection of and was able to show the malaria parasite inside the mosquitoes. And it just turns out that so he was recognized for this is his plaque in Calcutta, and he's working with the natives at that time. Now, again, right from the beginning, there are political controversies because his work was primarily in birds, where he was able to reproduce the malaria. Okay, but an Italian scientist named Giovanni Grassi had worked on humans and had proven that no, malaria is a transmittable disease with mosquitoes. But Rossi had, was a big propaganda person, so he was able to badmouth, the Italian scientist, and the controversy continued in the Nobel Committee, and finally an arbiter was given, none other than Robert Koch, who was a giant of bacteriology at that time, and the Brits won, and the Italians were left holding the bag. So politics was involved right from the beginning in Nobel Prizes. Okay, physiology and medicine, the various categories, microbes, vitamins, drugs, hormones, as we talked about, immunology. So these are all popular and goes in and out of fashion. And most recently, it's molecular biology and neuroscience. Okay, and various vitamins, which we talked about already, that initially diseases were thought to be due to parasites and infections, like malaria. And when during the Dutch colonies, people were getting sick with enlarged heart and heart failure and swollen legs, and that turned out to was suspected to be due to mosquito, but eventually some of the Dutch physicians who were working this, and showed that this was due to the rice that was polished rice that was given, okay, as opposed to brown rice. So the husk of the rice was, washed away. So the nutrition had a lot to do with it. So that was a foundation of vitamin B, vitamin, Eichmann. So vitamin B12, B1 was isolated. So, and why they were considered amines, A-M-I-N-E, amines. So that's how the name vitamin was coined. Okay, and so later on, the various vitamins, as you can just see from the litany, including the Hungarian scientist who inspired the lady scientist who got the COVID prize, with a difficult name of Albert von Szent-Györgyi. Okay, and so various, and vitamin K, which has to do with the bleeding disorder, was diagnosed. Okay, and sometimes, and the importance of nutrients in so-called fat-soluble vitamins was equally important, because people did experiments on giving just the protein casein inside milk along with sugar to animals, but they didn't grow. So that gave the concept that there has to be some nutrients which has to do with growth, and that was a discovery of vitamins. Later on, work was done. People were dissecting eyes of frogs, and based on that, they were able to isolate vitamin A. So the vitamins have a long saga and of interest to human health. And obviously, Robert Koch was the giant of microbiology. Again, along with syphilis, another important disease was tuberculosis. So Koch worked out what came to be known as Koch's postulates, okay, and which is the experimental method of not just isolating the organism, but culturing in outside the animal, reimplanting in a healthy animal, creating disease. And so this is so-called Koch's postulate. This is the foundation of bacteriology as we know it. Okay, not just, this is like the scientific method proven. And that's, and Robert Koch was a giant in his own ways, not just worked on the tuberculosis bacteria, worked on anthrax. And in those days, he traveled all over the world. He went to Egypt to investigate cholera, went to India, okay, and was a giant in his own field. Now, at the same time, the competition with the French continued. French had Louis Pasteur, and Germans had Robert Koch. So that controversy between the two nation states continued. Now, this, okay. Now, moving on to neuroscience, brain was difficult to diagnose on tissue, because in the old days when autopsy was done, brain was examined last. By that time, it was mush. And even when they stained with the regular stain, the red and blue stain, that the bacteriology, I think he did work with bacteriology, I think she knows, yeah. Okay. And so those stains did not take. An Italian scientist came up with the idea of staining brain tissue with silver nitrate. So the nerve cells showed up black. Okay, and now at that time the older school of thought was brain was just a network of bunch of fibers lying together. There were no cells inside the brain. But a Spanish scientist named Ramon Cajal, was an artist par excellence and a physician. So these are his exquisite drawing from looking inside, and he showed that yes, there were actually cells inside, and the branches, which are called axons and dendrites, branched out from the cell, almost 6 meters long. So these are his most beautiful drawings that looking inside a small microscope, he meticulously drew the artwork. He started out, he wanted to be an artist, but his father said you cannot make a living. So he became a physician, and he combined his passion for art as well as this thing. So these are Ramon Cajal and Golgi and Cajal. So Golgi, even during the Nobel Prize, did not believe that Cajal was right. Turns out Ramon Cajal was spot on. And that was the start of neuroscience. So all the neuroscience talk dates back to Ramon Cajal. And Paulo everybody knows about Paulo's reflex, and but his ethics-wise, he had a lot of lagging. He, not just tortured animals, but it was also not about, experimenting on orphan children. In the Tsarist Russia, there was no ethics committee, was rather slack. So he worked on orphan children and created holes inside their cheek, and then he started to make money out of selling gastric juices. And so Paulo, even though he was a Nobel laureate on ethic-wise, he has a really very dark history. And I have a videotape here on things, but for sake of time, I'm not going to be able to go too much into detail. And again, certain inventions have a huge impact larger than life. One that has is blood grouping, that was discovered by Karl Landsteiner about the antigen-antibody reaction. Okay, and he was lucky that he was able to find took blood samples from his colleagues, and was able to do the classic blood groups that we know about, A, B, and O antigen-antibody reaction that we know that he and so that was his big finding. And he also, and after initial work was done in Germany, then he moved to New York, and he continued working on varieties of blood group called rhesus, the Rh blood group. When during pregnancy it becomes important, and blood transfusions, changed the whole history of modern surgery. So one invention, along with DNA and penicillin and insulin, which we absolutely owe our modern lifestyle to, so, and on a personal note, he was Jewish ancestry, but for whatever reasons decided to convert. And the blood groups were used right away in paternity trial. Charlie Chaplin had a kid outside. One woman had accused him of fathering her baby. And Charlie Chaplin's trial he was proven that he was not involved, but he still ended up paying anyway. Okay. So that was the blood groups were used initially for paternity claims right away type thing. So that has been the groundbreaking discovery, in terms of, health and modern sciences. Now, as a cardiologist, I have to mention two of these things, that the tradition of experimenting on self has a long history. And a urologist resident named Werner Forsman, because in the early days, back in the 30s, they were thinking if you put anything inside your heart, the heart would stop. That was the ideology, because heart is a vital organ and you can't mess with it. But he challenged the orthodoxy view and talked a friendly nurse in helping him, and made a cut on his own arm and inserted a catheter from the arm inside the heart, and then walked over to X-ray department and took an X-ray. This was back in the 1930s. Okay, and that proved that heart did not stop. Okay, and that was the start of cardiology as we know it. Okay, and the German system was rigid enough that his bosses said, "You are going outside the discipline," and he was almost demoted. And then, unfortunately, he worked for the Nazis. Was a prisoner of war in Britain. And when he was interned in Britain, that's when he got the called that he had won the Nobel Prize. And so later on, after 5 or 6 years, he was released and went back to Germany to practice urology. So this was the start of cardiology as we know it. At the same time, everybody knew from the days of electric eel that animals have electricity. So human heart has electricity, but how to amplify the signal, it was done by a guy named Einthoven. He put the arms inside the saline jars and built a machine to amplify the signal. That was the rise of electrocardiography. Okay, and after several years, so the cardiology came into solid footing based on these two inventions. Okay, and at the same time, German dye industry continued to work, and this was the first dye that was successful against bacteria. Okay, and there was the sulfa group. They're not used anymore, but this was one of the dye, which he named Prontosil, and he used this, obviously before doing any trial. His own daughter had strep infection, and he used the dye and was successful. And the Nazis had prevented him from getting Nobel Prize and was rewarded several years later on, Gerhard Dome. So there was a start of chemotherapy. Okay, neuroscience has been very popular, and varieties of neuroscience, including Cahal, Sherrington, like whether the nerves are nerve transmission works on chemistry or electricity. There was a controversy, cables versus soup, that continued for a long time. Okay, it turns out, so there were two schools of thought that went on, but turns out both of them were right. Our brain and nervous system uses both electrical signal, which we can record on brain waves, EEG, and chemicals, which is called neurotransmitters. Okay, so both these discoveries are equally important. And a very personal, interesting story, a lady named Rita Levi Montalgini, and she was an Italian, worked in the fascist Mussolini, and was working in her bedroom on chicken eggs, and did an embryology about the nerve cell growth in chicken embryos. Later on, did pioneering work in something called growth factors in St. Louis. And she was in a class by herself. And she went back and became a senator in Italy, and was a giant in her own right, and was a huge person. So it's just the saga of Nazi immigrants who were chased out of Europe, continued. Okay, so this is, and obviously this was during the traditional Italy. So her father prevented her from going to medicine. She was a tough woman, continued, got her MD, and kept working in, so this was the story of Rita Levi Montalgini. Okay, so it's just the human interest story are fascinating to me as to how it plays a role. And obviously the discovery of penicillin, again, one of the biggest discoveries you can see. And this was surreptitiously discovered, Fleming was going on vacation for a weekend and left a Petri dish on the windowsill. Okay, and came back a few days later and saw, there was no growth in that area. Okay, and said, gee whiz, this is funny. And it turns out that it was a hot day in London. So somebody one ground floor below was working on fungus, and the fungus may have gone through the window and had settled on his Petri dish of his colonies. So just by sheer chance, and he published his paper in 1929, but didn't make much out of it. Later on, other scientists were working on in 1940s, came across his paper, and then the rest is history. During the war, treating bacterial sepsis was dramatically important. So the search was started as to how to grow this mold. Okay, and obviously, and the British scientists traveled all across the world, including the United States, and finally discovered the mold growing a luxurious growth on a cantaloupe in Peoria, Illinois. Okay, so Peoria has a lot to do with growing penicillin, and there was, notched up to mass production by American companies. And even though it was a British discovery, the Americans got the patent for it, and saved thousands of lives during the war. So this is a brief video for it.
British researcher Alexander Fleming, a laboratory scientist searching for weapons against bacteria, He's just beginning his career. When the
died from infection and died from direct bullet
Okay,
or
so
shell injury.
I think I'll send out this video so you
To
can.
cover all the plates. Fortunately, 1 or 2 remained uncovered.
But I told you the story already, so basically, so this is basically what just dramatizes it with actual footage of penicillin discovery. And again, even Fleming, to his credit, had said yes, that resistance could develop, but medical community and the world started using it as like candy. And sure enough, within few years, bacteria became. So this is the golden age of research that they every year a new antibiotic was discovered until the 70s, and we thought we had the infections cured. But alas, the antibiotic resistance is going to be the major issue as we get older. Okay, and Cold Spring Harbor Laboratory, which was notorious for eugenics headquarters, has had funded research of a lot of Nobel researchers. Watson and Crick will talk about people who were started out as physicists and marched on to biology based on the book by Erwin Schrödinger. Barbara McClintock, who came up with what is called jumping genes, transposable gene elements. Okay, she did her pioneering work. And again, a lot of times women get shortchanged. So her was considered, well, this doesn't make sense. But she, to her guts, continued to work, and she was proven absolutely correct. And the jumping genes has become the workforce that they play a huge role in causing diseases. Okay, and the classic, the genetic Nobel Prizes and genetics have a long history, starting from Morgan, who worked on fruit fly, Hermann Muller, who was one of his students, who saw that mutations can be caused by X-rays, and the aftermath of Manhattan Project, he was recognized for Nobel Prizes. So various other people, and we'll talk a little bit about Crick and Watson, who discovered the DNA molecule, and then Holly Corana and Nuremberg, discovered the genetic code of creating all the amino acids, because by itself DNA doesn't do anything. It has a code for proteins, and which letters code, the 3-letter code had to be. So people had to work that out. So Marshall Nuremberg, who was actually a University of Florida person, Hargobi Corana was an Indian immigrant in Wisconsin. They worked on it. And Sanger and Berg, which we talked about, the method of DNA analysis. Okay, and now another Nobel Prize, which initially made a lot of sense, was the different Mueller. This was Paul Hermann Mueller, who discovered DDT. Okay, and again, obviously, the mosquitoes were a big bane to humanity. Okay, and we started using it. It became widespread use for just about everywhere. Little did we realize that it had, toxic effects, and in some other countries it is still used. In the Western countries it's banned, and the lone voice who made against it was Rachel Carson about pesticides. Okay, and again, she was taken to task. Was considered to be the troublemaker by the DDT manufacturers. Okay, moving on. Some of the worst Nobel Prizes, this, I think some of you may know about it, but I won't assume it. Leucotomy, a Portuguese psychologist, named Moniz, had worked out, because mental illness was a difficult problem before the discovery of tranquilizers, and thousands of people were locked up in lunatic asylums. So by destroying the thinking part of the brain, the frontal lobe, he discovered a procedure called leucotomy. But here they just created, a very few number of people improved, become less agitated. But a lot of people ended up like zombies, including Caroline Kennedy, one of the Kennedy family's women. Okay, and Americans took that up with enthusiasm, and a neurologist named Friedman must have done about 700 or 800, went around teaching people all across the United States as to how mental illness can be treated by something called ice pick surgery. I mean, it just sounds gruesome when we talk about it, putting up an special instrument through your nose and destroying parts of the brain. And even though in part of the protest, that was recognized as a Nobel Prize winning discovery. And this is, Dr. Friedman, ungloved, showing surgery, how pounding this instrument through the nose, so it just almost gives you, it makes you nauseated. And again, the brash young scientist, who got the Nobel Prize, and the famous picture that you may have seen somewhere as to they created the DNA molecule based on the famous X-ray. That movies have been made about it. This was the X-ray was done by Rosalind Franklin, the famous photograph. She take the X-ray crystallography of DNA, because it is very hard to mount crystals, make crystals of this small molecule. She was a crystallographer par excellence and took the picture. It very clearly showed the double helix. And then she was working at University College London, and her boss, Maurice Wilkins, showed the photograph without her consent to Francis Crick, who was a physicist, Watson, who was a budding biochemist, okay, and they went on to build a model and we have discovered the secret of life. But again, this did not get the DNA code. So that was the groundbreaking discovery of 1953, along with insulin and penicillin. Okay, and this is the basic DNA code, so like a human being, a nuclear cell, DNA is on the genes are on the chromosome, wrapped around a protein called histone, and when it is unwound, all this DNA, 3 meters of DNA is wrapped around protein histone, and these are the A, C, G, and T, the DNA code. So this gives a basic idea of the DNA structure. Okay, and obviously, this is why he used the word central dogma. That is beyond my understanding, but this is the classic way the Francis Crick had said. And now and there was a race as to see how the various essential amino acids would be coded. Okay, and that's where the Corona and Nuremberg, did the work on it, and very quickly in 1960s discovered how the code, A, C, G, and T for and the first one was UUU was for tryptophan, the essential amino acid. Okay, and at the same time, obviously people were dying of kidney failure, and Joseph Murray and colleagues Thomas in Seattle were working on what came to be known as a bone marrow transplant. Okay, taking a blood cell from the donor, separating stem cells, because even after early birth, within few years, stem cells disappear, but they're still there in your bone marrow. That is constantly, so it can be harvested from bone marrow, frozen and transfused up. So that has been the book cure for a severe anemia, as well as for advanced blood cancers such as leukemia. So that's, and they've been the pioneer in bone marrow transplants since the early 60s. So eventually they were recognized for their discovery in 1990 for bone marrow transplant. And okay, and the brain imaging has always been a challenge. This was the standard way was X-ray, which just primarily shows the bone. Okay, and then later on computerized tomography, like taking a serial multiple X-rays and in sections. And this is the CT scan. The technology was discovered in 1979, and the funding was received from the Beatles EMI Corporation. Okay, so because Hunsfield and colleagues received the Nobel Prize in 1979 for CT scanning. And we'll talk a little bit about MRI, which is really a complex technology, which is the workhorse of neuroscience. MRA means a magnetic resonance angiography, where you can actually show the blood vessels. And last but not the least, you may recall from physics, we talked about positron, which was theoretically proposed by Paul Dirac and was shown 2 or 3 years later in accelerators. So that is used to discover the metabolism of the brain, as to how brain uses glucose for metabolism. It cannot use fat or protein. So this is the glucose metabolism that's shown. Brain uses sugar as energy, so that lights up with color. And this is a very expensive technology, but this is a precise way of diagnosing tumors or cancer cells. So this is the brain imaging technology that has evolved and has been recognized, rightly so. Now, and this is what I was telling about. The MRI technology is extremely complex, starting from the fundamental physics all the way to using it in for chemistry, because it has to do with your body is 80% water. So it has to do with, and when the atoms are subjected inside large magnets and then bombarded with radio waves, and then the magnetic field is stopped, the atoms of hydrogen, of water, go back to their original space. And based on the complex mathematics, images generated. So that's the principle behind MRI scanning. Okay, and that is the workhorse of of all sorts of body imaging. So it has dramatically altered. Getting back to cardiology, obviously we all knew that heart disease had something to do with cholesterol, dating back to 1950s. A small town outside Boston called Framingham did a lot of work. People have been studied for 5 generations and showed that cholesterol has a lot to do with your heart disease. But people didn't know as to how cholesterol was metabolized, and had to do with something called LDL receptors inside your body. Okay, and it's controlled with varieties of protein called ApoE and ApoE4 gene, which are for every protein there is a gene that are sitting on the surface of the liver, and the LDL that is taken with diet is engulfed by the LDL receptors and is released in the body. So the 2 researchers in University of Texas were working on a rare disease called familial hyperlipidemia. Means these are people who have genetic deficiency and they're born with extremely high cholesterol of 5 to 800 and get heart attack at the age of 10 or 20, and most of them die before 30. So, and at the same time, there are other people who are extremely low cholesterol. So they took cultured cells from this, and this is and tried to show as to what genetic abnormalities they had, and it's called LDL receptors. And based on this, on the other side of the word in Japan, people were working for various fungus, and a Japanese scientist had shown that one of the fungus, that they were working with had also lowered cholesterol in experimental animals. But the corporation that he was working for, we didn't want to pursue this. So they didn't, so he had to stop his research. His funding was, he was ordered to stop the research. And luckily, Merck bought that particular molecule, worked on similar molecules, and came up with purified the agent that was in that fungus. And there was a start called Mevalin. And that turned out to be the start of the statin therapy, or the drugs that some of you may be on, Mevacor and Zocor and rosuvastatin, that came out with a discovery from fungus. Okay, originally it was discovered by the Japanese Sanyo Corporation, missed the boat, and Merck was the first one who started making LDL lowering, cholesterol lowering therapy, and that has been amplified, and so that has revolutionized heart disease as we come to know it. Okay, I think you're moving along. And again, I explained the tendency of doing experiment on them yourself. Okay, Mechnikov, had, dating back to the 19th century, he had injected himself with fever. Bentinck, and had worked on it. People had injected themselves with varieties of organisms, and Gerhard Domag worked on his own daughter. Max, this is interesting story that as Americans often be interested in yellow fever, which was a big problem, during building of Panama Canal, and even in early colonial days in Philadelphia, the epidemic of yellow fever, was Benjamin Rush had to deal with it. And so it's another story. But Max Tyler, discovered the vaccine for yellow fever. And the famous Walter Reed did work in Cuba. Okay. And this was the first time people actually volunteered to be injected with yellow fever, letting themselves allowed to be bitten by mosquitoes with yellow fever. And they, sure enough, several of them died. So that was the first time people actually volunteered. And actually, the ethics is very, questionable. And Walter Reed's associate named guy named Lazar died of yellow fever. Some nurses who worked for the U.S. Army died, but none of them were recognized. And Walter Reed was the big name for Walter Reed Hospital. He never volunteered himself. Okay, so that's a story about yellow fever. And then a guy, a South African scientist named Max Tyler, worked on yellow fever vaccine, which has contamination from chicken embryos, and you can get some severe neurological side effects. And unfortunately, the vaccine has still not been modified dramatically. So yellow fever vaccine, it still has a substantial risk with it, and it is recommended only if you're traveling to endemic area. Okay, so there is a lot of tradition for self-experimentation. Again, I'm always fascinated by the people who had to rise from adversity. And another story similar to Rita Montalgini was Maria Capacci. He was like a 6 or 8-year-old kid during 1945 in Italy. He was separated from his mother's, went through various orphanages. After the end of the war, his mother was able to reunite. Fortunately, they had good connection and was sent to Philadelphia, okay, to work with a well-to-do uncle, and the rest is history. He worked on, went on to get MIT PhD, and worked on something called knockout mouse. This is not the knockout mouse that you were looking for. This is knockout mouse, okay, which is a workstone of stem cell research as to how the embryonic stem cells are cultured. And these are genetically pure, something called the knockout mouse. And that was Maria Capacci's discovery, okay? And the same discoveries were carried out with cloning and stem cells, and
which really opened up this whole approach that you might take a tiny bit of skin and generate cells of all other kinds from it. I work full-time and I have very expert colleagues to work with me. One is very fortunate, if the work goes fairly well, to find that recognitions come to pass. The one that everybody has heard of is the Swedish Nobel Award. My own activity is at the basic level, trying to find out how a cell which is completely committed to one kind of specialization can be switched into an entirely different one. As you can imagine, to take a small piece of skin and derive from it new brain cells or eye cells would be an enormous health advantage. If people are receiving their own kind of cells, there would be no need for immunosuppression. Disorders like neurodegeneration, Alzheimer's and so on could be relieved. That is indeed the direction in which the work is going.
Okay, so, and this takes away the ethical consideration for embryonic stem cells. So this is called the induced pluripotent cells. Okay, and he has to be the Nobel laureate with the best looking set of hair. Sir John Gudrun, you can just see how his, is a pro. And now at the same time, the problem of creating induced pluripotent cells was worked out by two scientists, and as the mystery goes on, Shinji Yamanaka and another scientist, named Thompson, who worked at University of Wisconsin. And now this is, John Gudrun's discovery was, he did the experimental work here on, taking a cell, from skin cell and cloning, it's like how creating the clone. So there was a pioneer in, the famous sheep dolly. On the other hand, Shinji Yamanaka was working on regular cells and introducing he had isolated about 24 genes and selectively to try eliminating one after the other by introducing with virus. Narrowed it down to about 4 genes that were essential for converting a regular cell into what we call pluripotent cells, like from skin cell. It's just like a mother telling a child, when you grow up to be, you can be anything that you want to be, including the president. The same way, a skin cell can be turned into brain cell, liver cell, kidney cell. So these are called the Yamanaka factors. So these are just 4, don't bother with what they are, the genes, the names don't matter. They're called they're transcription factors. So these are the proteins that, control other genes called Yamanaka factors. And so this took all the wind out of the ethical consideration for embryonic stem cells. Okay, and so this was another important prize was the targeted cancer immunotherapy. This just opened up the floodgates of the two types of, how the T cells have mechanism as to how to recruit them but there are various receptors on the cell that by inhibiting those receptors, because if you have T cells are suppressed, these are the immune cells called, there are varieties of immunology cells called T cells and called dendritic cells. So by inhibiting the receptors on the surface of the cells, PDL1 and CTL4, we can stop the growth of the tumors. Okay, and so this is the two people who work separately on it. And there was a start of what we call targeted chemotherapy, Tasuku Hinja and James Ellison, and he works in Texas. And so this has changed, and this is some of the chemotherapy that Jimmy Carter received for his melanoma. Okay, and there was a groundbreaking discovery as to how instead of just giving out a blanket toxic drug which could damage all the other tissues, so this was the Nobel Prize for 2018, okay, for targeted immunotherapy. So now we can just ask ourselves, have the pace of research slowed from classic? Because in the first 100 years, there were some dramatic discoveries that took place. You can just see how, including even in, human origin, okay, as the pace slowed down, perhaps to some extent, but the answer is still, is anybody's guess. And again, what happens sometimes, it's a Nobel Prize when the people win, they're afterwards, somehow being a celebrity, the work slows down, so that's a food for thought. Okay. And then again, sometimes they go off their rocker, so to speak, and come up with various crazy ideas, as I give some examples of it earlier, okay, including homeopathy denial, COVID denial. So just being a Nobel laureate gives the people bragging rights to expressing opinion on fields. And to the credit of one scientist who worked on prion diseases, was a child abuser and actually had the dubious distinction of ended up in jail, okay, and served like several months as a child molester, okay, and there is something also called the Ig Nobel prizes, okay. These are the people, it's totally useless research that is tongue-in-cheek, that is recognized, okay, and this is you'll get a kick out of it, that the people, one person, two scientists have gotten both Ig Nobel Prize and Nobel Prize. Before things we were talking about graphene, which is, the carbon shades, they have received the Nobel Prize just 1 year after their paper. But they had also received a Nobel Prize for suspending frogs with magnets. So they had the dubious distinction of receiving both Nobel Prizes, and including the well-publicized Deepak Chopra had received the Nobel Prize. L. Ron Hubbard, why toast falls on the buttered side. So there are varieties of crazy things. That's a tongue-in-cheek award that is given in Boston for Ig Nobel Prizes. Okay, the absurdity. Okay, and that is, again, we already talked about how it is limited to 3 people. Now, the important thing is we are in Berkeley, California. Parking is so difficult. So Paul Mutter, who discovered the runaway universe, the biggest benefit of winning Nobel Prize, he gets his own parking spot at Berkeley. Okay, so this was, okay. Now, and so these are some of the other stuff that I had seen, and there are some other prizes that are trying to make up the deficit of Nobel Prize, something given by Crawford prizes that is given in other disciplines such as astronomy, mathematics, by the King of Sweden. Okay, and I already had talked about this. Okay, a few more slides. It's about the so-called fundamental prizes, or this was started by a Russian physicist and tech billionaire named Yuri Milner in 2012, starting out with physics, and then later on was renamed as Breakthrough Prizes with the help of Zuckerberg, Facebook fame, Sergey Brin, Google fame, and Wojcicki. She is the head of the 23andMe, Priscilla Chan, and a Chinese tech billionaire. This is given in varieties of categories: life sciences, fundamental science, mathematics. And they have the glimmer of combining Hollywood, Silicon Valley, and science. And the very first year, they recognized people who are part of the selection, including Eric Lander, who was part of the Genome Project, Robert Weinberg. He's kind of a giant of cancer medicine. He discovered something, he proposed something called the hallmarks of cancer, which is one of the most well publicized papers, and he had done a fundamental work in. And there's a variety of people who have worked on, on cancer medicine, and I think I'm just going to show this thing. No, and Dr. Malone worked on the Parkinson's disease stimulation of brain, the deep brain stimulation. Okay, all right, and then some of them have gone on to got Nobel Prizes, including Japanese scientists for cells that destroy themselves, called autophagy. Okay, and now this is interesting how that nucleotides can be given for the gene that is deficient. So
very quickly after learning about the disease, learning about the molecular mechanism, I thought this is something that we have to work on.
He called me up one day in 2004 and agreed to start collaborating. My lab, we've been interested in a process called RNA splicing. It's understanding the basic workings of the cell and how genes function. And our initial collaboration was how to use antisense technology to modulate splicing in ways that might have therapeutic benefits. Within some time after that, we began to focus on spinal muscular atrophy.
Adrian is doing a lot of the basic biology behind the project, and we were doing work to better understand how to deliver the drug.
Oh my goodness, look at you! Are you standing like a big girl?
What our technology is based on is designing small pieces of nucleic acids, and they're designed to bind to the RNA intermediate molecule and modulate it. And that's what we're doing for SMA, is we're altering the function of the RNA so that it makes the protein that we want it to make.
Since she's gotten that first injection, not only has the disease stopped, but she's gotten stronger.
We're not just stabilizing the disease, but they're actually improving. This is my first experience where I've worked on a drug that had this big of an impact on a patient.
Still brings tears to my eyes. It's a miracle.
Now, this is an extremely rare disease, 1 in 100,000, and this is called oligonucleotide therapy. So it's specifically designed to correct the deficiency of the gene. Now, I'm glad you're all sitting down. The cost of this drug is $750,000. So it's the most called Nusiran. It's the most expensive drug in the world. But it does work. Okay, how the society is going to pay for it, your guess is as good as mine. But it is, it is marketed for, and it is given through spinal injection. So this is the biggest discovery, and it is extended for other diseases also. Now, at the same time, this quickly diagnosing the genome structure is important. And the two scientists at Cambridge, at their famous pub in Cambridge at Cavendish Lab, came up with the idea of something called the Oxford Nanopore technology. So it's almost like a USB stick where you could do the DNA analysis. And this has been successful enough. It has also been used in space. People used it on space shuttle and were able to do DNA analysis out in the field. And this is one of the earliest reasons why they were able to do the COVID genome, the COVID virus sequence. So the Oxford Nanopore technology was recognized as a breakthrough prize in life sciences in 2012. Shankar Balasubramaniam and Kelly, who were, David Kleinman, using fluorescently labeled nucleotides with a single molecular level to do the DNA analysis. So it's a groundbreaking discovery. Now, this may come as a, probably 2011, there was a company called, 2016 election, a company called DeepMind was considered, they did the targeted election targeting, and they've also worked with something called AlphaGo, artificial intelligence technology, that defeated the Chinese Go players. And recently they worked with something called AlphaFold, which this detects the sequence of the protein. And this is a genius who is, Cypriot Brit, and was a chess prodigy to start with. and had worked on neuroscience, computer science, and founded a company called DeepMind. Okay, and that they are on the forefront of
community, opening a path. How to predict the shape of a protein from its genetic sequence. Then 2 years ago, scientists at DeepMind, whose machine learning system solved chess and Go, revealed AlphaFold, an AI that solves the protein structure prediction problem. And they gave it free to the scientific community, opening a path that promises new vaccines, therapies, nanomaterials, and a far deeper understanding of the nature of life. For developing an AI that accurately predicts the structure of proteins, Demis Hassabis and John Jumper win the 2023.
So, and now this company is bought out by Google. Okay, so they are part of the Google empire.
Breakthrough Prize.
Okay, and this group. Now, obviously, we talked about genetics. Sickle cell disease is common amongst people of African ancestry. The same way, cystic fibrosis is very common in people of Northern European ancestry. And if there are mutations that take place,
disease affecting the lungs and other organs. The cause is a malfunctioning protein, a kind of gatekeeper that lets salt in and out of cells. Determined to find an effective treatment, a team of scientists searched thousands of molecules for one that could fix the gatekeeper protein. Finally, they found one. Then they found more and developed them into a combination of treatments that are now improving and extending lives around the world. For life-transforming drug combinations for cystic fibrosis, Sabine Hadida, Paul Negulescu, and Frederick Van Goor win the 2024 Breakthrough Prize in Life Sciences.
So this was, a dramatic thing, because cystic fibrosis, otherwise, when I was in training, people lived to be barely 20 years old. But this mutation is only a certain people with cystic fibrosis have this mutation. But again, that's a big advance in the treatment of a very potentially lethal disease. Okay, and again, they were ahead of the game for the Nobel Prize. Obviously, a lot of you may recognize that these were the two people.
Anyone else got that feeling? A frozen time. A time of waiting.
Okay.
The course of human progress.
Oh, okay, I'm sorry. This is a
century. Humanity learned to read it one chemical letter at a time.
Yeah, this is not. This is not this is talks about the people who did not. But Caitlin Carrico and Drew, they were pioneers of the mRNA vaccine. I think that's the next one.
But
okay, so that was that was the Nobel Prize for developing the vaccines, and this were people who did the skin the receptors for pain and touch. Okay, a guy named David Julius, and they work with. Okay, let's play.
Found in nature affect our senses, from the mind-altering power of poisons and painkillers to the heat of a chili pepper.
I've always been fascinated by natural products and how plants and animals have evolved to make chemicals that we can exploit for research and to understand the biological world. Natural products give us chemical cues that we can use to hack into the nervous system to understand how it works. I think what's fascinating about sensory systems is when you come to realize that every animal sees the world in a different way. How does a snake see the infrared world? How does a shark detect electrical fields to navigate through its environment? We've used natural products like capsaicin, which is the pungent agent in chili peppers. It's a sort of chemical probe to identify molecules in our body that are involved in pain sensation. Sensory systems enable us to construct an internal representation of the external world.
By understanding the fundamental mechanisms of pain sensation, Julius is pursuing a path that could lead to new treatments.
Okay, so this was, the discovery of the pain sensation genes, and pressure sensation genes. Okay. Now this is absolutely worth seeing type of thing. Now just stick around for a few more minutes. This is a little out of sequence, but this is a technique of using light to control cells. Okay, and the two guys who are they started our work at Stanford and then at MIT. Okay.
Off specific sets of.
Okay, let me go.
In a brain circuit, you have neurons of many different kinds. And so if you really want to understand how a brain circuit computes, ideally, you would be able to turn on or off specific sets of cells and see how they influence their neighbors. With optogenetics, we wanted to get a gene that we could just borrow from one organism and plop it into a neuron and make it light activatable. So Carl and I started experimenting. Carl put the genes into neurons. I would then activate them with light. And we found that one of these molecules, which comes from algae, if you put it into neurons, you could activate those neural potentials with light. In many psychiatric conditions, such as schizophrenia, autism, bipolar disorder, the changes in the brain are so subtle. With optogenetics, we can pinpoint exact cell types and exact pathways in the brain that, if they could be the sources of new drug targets, if they could be the sources of electrical stimulation targets, could potentially help a large number of patients. Perhaps we could then start to answer questions like, who am I, and what is my identity, and what should I do, and why am I here?
For the development and implementation of optogenetics, the programming of neurons so that their electrical activity can be controlled by light.
The Breakthrough Prize is awarded to Ed Boyden.
So this was, this was like the discovery of the decade, so to speak, by Nature magazine, optogenetics. So there's a lot of excitement. Okay, and again, people with CRISPR were recognized before they got the Nobel Prize. So this is the same. This thing. So 2015. So again, 5 years before they received their Nobel Prize. Okay. And these are some of the earlier ones which we talked about, hallmarks of cancer. So this is the little out of sequence thing, sorry, but 2013. Okay, and I think I just have a couple more. Okay, now I think one or two breakthrough prizes in physics are worth mentioning, and this is the Event Horizon Telescope.
Readings. Local gravitational fields are increasing exponentially. Everything says we better get the hell out of here. It will be visible again in 4.
The numbers of real-world technologies inspired by the imaginary universe of Star Trek are pretty impressive. Kirk's communicator became the flip cell phone. My crew used tablet computers on the Enterprise before Apple invented the iPad. I'm pretty sure they owe me money. And scientists and technologists are working to turn Geordie LaForge's visor into prosthetic devices for the blind.
I believe that science and technology and the
They
exist. So the question is, how do you see the unseeable? Because black holes are cloaked in this gravitational invisibility region. You realize that all the gas and dust flowing onto the black hole superheats in a cosmic traffic jam, heating itself to billions of degrees. So what you're looking at is essentially light from behind the black hole being bent in an extreme way around just before it disappears through the event horizon. The event horizon is the point of no return, the region where gravity is so strong that even light can't escape. In order to capture this image, we had to have the angular resolution that's equivalent to being able to read a newspaper in Los Angeles while you're standing in New York. So to do this, we had to build a telescope the size of the Earth, and that is what we did. From Spain to Hawaii to Arizona to Chile to the South Pole. You need telescopes around the world, all operating at exactly the same microsecond. You need teams of people at each of those telescopes. People had to come together. Countries had to come together. Ideas had to come together. And this took over a decade. There was never any moment when we were 100% certain that anything would work. We like to say it as if we jump off cliffs and invent parachutes on the way down. We're uncertain, but we're confident enough in the team that we were going to be ready when opportunity presented itself. And that's what happened. We have seen and taken a picture of a black hole. We asked the deepest question. We'd seen the unseeable.
Okay, so this is what Stephen Hawking had proposed, the event horizon, and that there's a black hole, but he had passed away before this picture was taken. So obviously, so that was what he had predicted based on theoretical basis was actually proven. Okay, so that was the Event Horizon Telescope. Okay, because nothing can escape, so that's what they were able to take the picture. Okay, And again, this is the runaway universe. So that was that was a Nobel Prize, and I think this is probably my last slide. Okay, and okay, and this is I'm like this is almost too complicated. I'm not even going to get into it, type thing. So this is to do with information theory and other stuff. So I think it's a little too complicated for most people, type of thing. So, and the mathematics Nobel breakthrough prizes are very complicated as to what they discovered. So I think it's above my pay scale. So I'm not going to bother covering with that. So we have, and there's, and these are the people who had worked on information theory and multiverse. So it's a very, gets, really up, a lot of it is theory and ideas, which are not worth discussing on. So we've covered, all the three major categories. And I think I've tried to give a bird's eye view of how, starting from Royal Society to all the way, to taking pictures of black holes and curing life-threatening diseases at extreme cost. So we have given a whole journey as to how we've come a long way from Isaac Newton to curing rare diseases such as spinal muscular dystrophy and taking pictures of the sky. So we have covered about, we went through. I didn't go for a break because I wanted to make sure I finished this. So I will stop my screen share and send out the recording. Thanks for sticking around, people. It was fun.
Thanks, Brett. Yes, it was fun.
Yeah.
Thank you.
Yeah. Okay. All right. Nice meeting you, Rex, and hopefully we'll meet you in person someday. Okay.
Yep, that sounds good. I hope so as well.
All righty. Okay. And
really enjoyed it. Thank you.
I'll send out the recording type of thing. And actually, here is the thing, because I think I was thinking about doing an extra session, but I went over with so-called bird's eye view. And what I have done is recorded all of this on detailed lectures on medicine and breakthrough prizes. And I will send out the links for it. So those of you who are as geeky as I am can watch it. Okay, and they're free, because I'm just going to put it on YouTube link, because if I send out through through Zoom, it will expire and you have to download and you have to go through, enter that complicated password and other stuff. So I'll just send out the links in an email.
Have you monetized your YouTube channel, Brett?
Oh, heavens no. I don't want to see. I mean, like, if they show ads, I mean, that's fine. But and actually, this is interesting that when you put the YouTube link through YouTube, the copyright does not seem to come into the way. Okay, they don't rap on my knuckles that, hey, you're violating copyright. So you can just, I figured out how to put the YouTube link and put the insert thing. So all of these are YouTube videos, 2-minute videos from, or maybe they're not commercial, so they're educational. So, because I don't think I can show Monty Python, because that would be copyright. And BBC is pretty strict about it. One time, I think my video said, "Oh, cannot be shown in this country because it violates copyright or something."
Yeah, you have to VPN to a server in the UK, and even then, there's the risk of the licensing van driving by your house and wanting your 150 quid.
Yeah. Oh, yeah. I think that. So that, no, but I mean, that's that's one of the ways I think it's different societies do different things. So no, so I think, but it works out. So at least and it is easy to upload. I finally figured it out how to do that. I think so. Okay, and so I'll send out. So if you're interested, because the breakthrough prizes, they have a very nice website. They have the people who are awarded, what they did, and in just 2 minutes summarizing how they showed about. Because otherwise, nobody's going to look at cystic fibrosis, metabolism, type thing, okay. I mean, unless you're really working in the field, so. Okay.
Thanks a bunch, Brett.
Okay, fine, it was fun. Okay, thank you, gentlemen.